Okay, here we go. This is the last slide and the last problem for this particular unit. The common ion effect. We'll explain what that is as we get further along in this situation. It says we got a saturated solution of silver chloride. Let's talk about what silver chloride is. It's AgCl, it's a solid, but a saturated solution is going to produce a few ions of Ag plus, and it's going to produce a few ions of Cl minus. It's a saturated solution. That's a code word for us. Anytime we see the word saturated, you should automatically think, oh, we're at equilibrium. Oh, these two ions should be in a 1-to-1 ratio with one another. And they are. But instead of putting X and X in for Ag plus and Cl minus, they tell us what Cl minus is. They tell us it's 1.34 times 10 to the minus 5 molar. And again, because it is a saturated solution, we can assume that that is at equilibrium. Here's the tricky thing that a lot of people miss out on. If Cl minus is 1.34 times 10 to the minus 5, and I'm at equilibrium, then Ag plus is also 1.34 times 10 to the minus 5 molar. Okay, so we have just answered the question given in A. Then in B, they say, what's the KSP? They're not asking us to look it up. We're supposed to calculate it. KSP, as you'll remember, is equal to the concentration of Ag plus times the concentration of Cl minus. So in this particular case, I can just put in 1.34 times 10 to the minus 5 twice. Or I could just square it, right? Same thing. So if I do that on my calculator, let's see what it comes out to. 1.34 E minus 5 and then squared. And I get 1.80 times 10 to the minus 10. 1.80 times 10 to the minus 10, that, my friends, is the KSP of AgCl. Now, let's get to the meat of the slide, the common ion effect. You know, when we put AgCl into water, we get Ag plus and we get Cl minus. What happens in the common ion effect is instead of just putting it into water, what if you put it into a solution of something else? So if I read part C, it says silver chloride is allowed to reach equilibrium in a solution that contains 0.1 molar NaCl. I'm going to stick with the same reaction that I wrote before. So you'll notice it's really important. I'm not writing NaCl as a reactant in this equation. It's not, but it does have an impact on this equation. And let's talk about how that is. There's something in here that's called the common ion. What you have to ask yourself is, between NaCl and AgCl, what is the common ion? This is not a trick question. It means, what do they have in common with one another? They have in common with one another Cl minus, right? They both have Cl minus in them. And in this particular case, we have 0.1 molar NaCl, which means we also have 0.1 molar Cl minus. That's a huge amount of Cl minus. If we were to use Le Chatelier's principle to demonstrate what would happen in this particular situation, what you're doing is essentially spiking the solution with Cl minus. That's our stress on this particular equilibrium. And what do we know? We know that when you put a stress on a system, the system responds in the opposite way. So the system is going to try to get rid of Cl minus by reacting it with Ag plus and sending those ions to form more solid. So we'll produce more solid. We're not increasing its concentration, we're just making more of that solid. And so the question becomes, what happens to Ag plus and its concentration at equilibrium? Well, we know that Ag plus is going to go down from where it was. But the question is, how much does it go down? Well, here's how we're going to answer that. We know that Ksp is equal to the concentration of Ag plus times the Cl minus concentration. Normally, these would be X and X, right? But here, we know that we have just spiked this with a gigantic amount of Cl minus. So I'm going to plug that into this equation right here for Cl minus. And we're going to say that we're going to get X amount of Ag plus in solution. That's going to go there. And we already have our Ksp value because we calculated it up here. So in other words, I'm going to have 1.8 times 10 to the minus 10, my Ksp value, is equal to the concentration of Ag plus, which is X, times this new spiked concentration of Cl minus, which is 0.10. Okay? If you do your math on that, it's not too hard, but let's do it. If I take 1.8 times 10 to the minus 10, and I divide it by 0.1, I get a very, very small number. I get 1.8 times 10 to the minus 9, right? That's X. X is Ag plus. And Ag plus is now 1.8 times 10 to the minus 9 molar. That is a tiny number. What was it when it was in just plain old water? It was times 10 to the minus fifth molar. Now it's times 10 to the minus 9 molar. So by adding a common ion, in this case Cl minus, what we did is we just reduced the equilibrium concentration of Ag plus while at the same time making more solid AgCl. Let's come back and let's practice a problem similar to this one.